In this study, I have built an MRI simulator. The nuclear magnetic resonance phenomenon relies on below equations, which is given here. So, by solving these equations, one can actually get the magnetization of any tissue for each time t. However, there is no analytical solution for this equation. So, we simulate these equations to get the image that we want. Here, B0 is the constant magnetic field, GT is the gradients, and B1 is the RF field. In this study, I've considered only three parts for the simulation. The free precession, there is no RF excitation and active gradients. The RF excitation which is used to tip the magnetization, there is no relaxation caused by T1 and T2, and the active gradients only for moving around the K-space. During the free precession, the equations are simplifying to this one. By solving these, we can actually get the analytical solution and get these magnetizations. So mt is actually equal to the relaxation parameters here times the rotation matrix caused by the off resonance effects delta omega and however much time passed, and the initial magnetization. So if the initial magnetizations are known, then we can actually get the exact image. The second one is the RF excitation. During the RF excitation phase, the equations are simplifying to these one by omitting the relaxation caused by the T1 and T2. However, there is no analytical solution for this one. And in the literature, it is widely used to just simply assume that these actually just tip the magnetic field. So I've just did that. So I assumed that there is a pulse sequence, and at specific times there is theta 1 and theta 2, and this pulse is repeated. So the exact analytical solution then becomes only a rotation given an initial magnetization, as in this one. It can be either in X, Y, or Z direction. It can also be the spoiler gradients, which can be used to kill the transverse magnetization. And finally, there is active gradients used in imaging. So it is only used to move around in K-space. But this also creates, the delta omega here creates a chemical shift due to off-resonant effects, which I have incorporated in the simulations. For the simulations, I've just used this linear forward model. So this is actually a linear forward model. There's an MF forward model times the initial magnetization and an offset. This is equal to MTR. MTR is actually equal to M0. So by solving this inverse relation, we can get the magnetization that we want. For this purpose, I have simulated through each RF pulse. I've pre-processed it and then calculated the RF tip matrix. I have done this for each tissue, and by calculating these, I've calculated the M0 and then calculated MTE at echo type, and then calculated the chemical shift, added it, and there's also an effect caused by the non-ideal RF pulse. So it's a finite duration RF pulse. It actually corresponds to a convolution. So this is also incorporated, and by Gx and Gy we can actually downsample the image. So the usages as such: there is a simulator here, and we can simply set these parameters to get the any pulse sequence we want. I'm just gonna skip to the results. So I've used these parameters to simulate for each tissues, and then I've multiplied each tissue by its density. So by TE equals 10, 20, and 30, we can get these images. And then this is a T2 weighted image. This is a T1 weighted image with these parameters. And actually we can simulate more complex RF pulses. So this is like an X, Y, X, Y, X, X with different angles. And this is the resulting image, the magnitude and the phase. And different TE results in different images at the left and at the right. We can also simulate a gradient spoiler here, as in here. So when we use such a pulse, we get the image on the right. If there wasn't any spoiler, we wouldn't kill the transverse magnetization, then we would get a complete desaturated image. And finally, this is a spin echo image with TE equals 120 milliseconds and TR is 1000 milliseconds. Next, we simulate the noise and the effect of the finite duration of RF pulse. So for a finite duration of RF pulse, there is actually a blur effect, as in the ones in the left, and when we give also the SNR, there is noise, as in the images in the right. So the original images are clear, but this one is more blurred compared to those. So in this study, I built an MR simulator. The simulator can handle multiple types of RF pulse sequences and create images accordingly. So let me give an example, as in here. So when we want to simulate such an RF pulse, as in here, we just set these flip angles, directions and pulses, and we can actually get the image we want just by simulating through these. So this is the corresponding RF pulse of this equation. We can actually kill the RF pulse in here. So in this case, we would kill it early, and then it would still look like this one. Thank you for listening to me. It would be clearer as in this one. So thank you for listening to me.